Welcome back, everybody. It is our last chapter of this semester, all about absolute value and piecewise functions. So we're going to start with just what is an absolute value equation and how do we solve it? An absolute value equation has at least one absolute value expression. A few reminders of absolute value. Absolute value always has to be greater than or equal to 0. So we can have the absolute value of -4, which is 4. Is 4 greater than or equal to 0? Yes. The absolute value is 7. Is 7. Is 7 greater than or equal to 0? Yes. Now, I know we talked about this way back at the beginning of the year, but a reminder that absolute value is the distance from 0 on a number line. And so that's why it's never negative. It's a distance. You can't owe distance. The second property, if we say the absolute value of -8 has to equal the absolute value of 8, well, that's true because the absolute value of -8 is 8. The absolute value of 8 is 8. Does 8 equal 8? Yes, it does. If I have, let's say, -4 times 5, that should be equal, if we separated that out, to the absolute value of -4 times the absolute value of -5. The absolute value of -4 times 5 is the absolute value of -20, which is 20. The absolute value of -4 is 4. The absolute value of 5 is 5, and 4 times 5 is 20. Does 20 equal 20? Yes, it does. And then whatever we can do with division or multiplication, we can still probably do with division. So if I look at this last property, it's saying if I wrote the absolute value of -18 over 9, we can rewrite that as the absolute value of -18 over the absolute value of 9. -18 over 9, if I left it as just a regular fraction, is -2. And the absolute value of -2 is 2. If I separate it, the absolute value of -18 is 18. The absolute value of 9 is 9, and 18 divided by 9 is 2. So we still get 2 is equal to 2. Pause for a little bit, take down these steps. We can graph the solution on a number line with closed dots because of the equal to. And then we just need to, again, refresh our memory that absolute value of anything cannot be less than 0. Okay, cannot be less than 0. That's probably the first thing that you should always check is our absolute value equal to either 0 or a positive number? And then the other thing, just to refresh our memory, is when you multiply or divide by a negative, if we have an inequality, the sign switches, the inequality sign switches. We shouldn't really have to worry about that for most of what we're doing, but just as a reminder, if we doesn't have anything to do with absolute value, only with the inequalities, if you have a greater than or less than, and things like that. All right, so our examples. First thing we need to do is check to make sure our absolute value is all alone, meaning there's nothing touching either side of the absolute value symbol itself except an equal sign. And that's true here, so we're good to go. Then we want to check what it's equal to. That value has to be greater than or equal to 0. 6 is greater than or equal to 0. Now that I've checked those two things, then we say x minus 4 is equal to 6, just like it says, without the absolute value. And then we say x minus 4 is equal to negative 6. And the reason why is because we have absolute value. So what numbers are 6 units away from 0? Positive 6 and negative 6. Once we've written our two solutions, or equations, then we solve for x. The opposite of subtracting 4 is adding 4. That adds to 0, so we're left with x is equal to 10. The opposite of subtracting 4 is adding 4. We have x, that adds to 0. Negative 6 plus 4 is negative 2. And so we have x is equal to 10 and x is equal to negative 2. So if I were going to graph that on a number line, there's negative 2 and there's positive 10. And that would be it. Example 2. Always starting with is our absolute value alone. There's nothing touching either side of it except the equal sign, which is true. And then we check what it's equal to. It's got to be a number that's greater than or equal to 0. Well, negative 5 is not greater than or equal to 0. So this one has no solution. I can't even start it because there's no way for absolute value to be equal to a negative value. Number 3. Now I see that it's equal to negative 4, but here's our absolute value equation, and there's a minus 10 touching it. So our first step is to move that 10 over. We're going to add 10 to the other side. So we have the absolute value of 3x plus 9 is equal to 6. Now if we look, our absolute value symbols are alone except for the equal sign. And it's equal to a positive 6, which means it's good for us to go ahead and solve this. 3x plus 9 is equal to positive 6, and 3x plus 9 is equal to negative 6. Subtract 9. That adds to 0. 6 plus negative 9 is negative 3. Bring down our 3x. That adds to 0. Negative 6 plus negative 9 is negative 15. Our last step is to divide everything by 3. That reduces that to 1x. Negative 3 divided by 3 is negative 1. 1x. Negative 15 divided by 3 is negative 5. If I were to plot this on a number line, then I would plot a dot at negative 5 and negative 1. Not doing any shading or anything like that because this is not an inequality, it's an equal sign. So we only have those two exact answers. All right, if you would try number 5, 6, and 7. We are going to skip 10 and 11 and go straight to the next set of examples, which are 12 and 13. So if you would take a few minutes to jot this down. All right, let's take a look and see what that meant. We're going to still want to have this set equal to two equations. We still pull out that 3x minus 4, and we're pulling out that x. Then we have 3x minus 4 and then we still have the negative part of that as well. So it's really no different than the other ones without the absolute value. It just changes things a little bit when we get to something like 13. So if I'm solving this for x, I'm going to take 3x to the other side. The opposite of a positive 3x is a negative 3x, so I'm subtracting 3x. This adds to 0. We have negative 4 is equal to 1 plus negative 3 is negative 2x. These add to 0. We have negative 4 is equal to negative 1 plus negative 3 is negative 4x. Solve the equation on the left by dividing both sides by negative 2, and the equation on the right by dividing both sides by negative 4. That gives us 1x is equal to positive 2, and 1x is equal to positive 1. 13 is where we see it just a little bit different. Again, we take out the absolute values. This 2, the absolute value, will act kind of like a parenthesis. And then we have the 4x minus 10 is equal to, and we have a negative this time. So just like we had the positive and the negative with just the numbers, we do the same thing with our absolute value that has them on both sides. It's the same process. We just have probably a little bit of extra work to do with the distributing. So I'm distributing 4x minus 10 stays. 2 times 3x is 6x, and 2 times 1 is 2. Again, this 4x minus 10 stays. Negative 2 times 3x is negative 6x, and negative 2 times 1 is negative 2. Now we work to get our variables on the same side and then our non-variables on the opposite side to solve. I'm going to move this 4x. The opposite of a positive 4x is to subtract 4x. Don't forget that minus sign with the 10. So we have negative 10. 6 plus negative 4 is 2x. And then we bring down that plus 2. I'm going to subtract the 2 over for its like term. Negative 10 plus negative 2 is negative 12. We bring down the 2x, and that adds to 0. Divide by 2 on both sides, and we get negative 6 is equal to x. For the equation over here on the right, I'm actually going to add the 6x over because the opposite of a negative 6x is a positive 6x. So 4 plus 6 is 10x. Bring down the minus 10. Our 6's add to 0, and it's equal to negative 2. Add 10 to the other side. That adds to 0, so we have 10x is equal to 8. Divide both sides by 10. That reduces to 1x. 8, I can't divide 8 by 10 evenly, but I can reduce that fraction to 4/5. So our two solutions would be negative 6 and positive 4/5. Please try number 14. Pause for a minute to jot down these special solutions. So an extraneous solution, we've done all of our math the right way. But sometimes, even when we've done the math correctly, 1, 2, 3, however many answers we get, there's a chance that 1, 2, 3, or all of them do not work when you plug them back into the equation. So let's take a look at what that seems to be. I'm going to do example 16 just the way that we've done all the other ones. So we check that this is all alone with the exception of the equal sign. That's the case. 2x plus 12 is equal to 4x. And then remember, we take this and use the negative of it. 2x plus 12 is equal to negative 4x. I'm going to move the x's together. The opposite of a positive 2x is a negative 2x. So I'm subtracting 2x for both equations. Adds to 0. Bring down that 12. 4 plus negative 2 is 2x. These add to 0. Bring down the 12. Negative 4 plus negative 2 is negative 6x. To divide this right side by negative 6, so we get x is equal to negative 2. Divide the left side by 2, and we get x is equal to 6. All right, so we got two equations. But if I plug these in for x to check my solution, this is what happens. I'm going to start with the 6. So we have 2 times 6 plus 12 is equal to 4 times 6. Well, this is 12 plus 12 is the absolute value of 24. Is the absolute value of 24 equal to positive 24? That's truth. Now, if we take a look at the negative 2, 2 times negative 2 plus 12 in the absolute value, and then 4 times negative 2 on the right side. 2 times negative 2 is negative 4. Negative 4 plus 12 is 8. So we have the absolute value of 8 is equal to 4 times negative 2 is negative 8. Now here's where our problem is. I have an absolute value equaling a negative value, and that's never going to happen. It can't happen. And so that's what I mean when I said we've done our math correctly. Negative 2 is an answer. We did all of our work. But when I plug it back in, it does not work with the type of solution or equation that we're working with. And so I cannot include negative 2 in my answer because it is extraneous. And so we mark negative 2 as extraneous, and the only answer we would actually give is x is equal to 6. The other type of equation that we'll run into looks like number 17. So we know that we're taking x plus 5, and we use x plus 11, and then x plus 5, and negative 1 times x plus 11. We have the positive and then the negative. If I distribute over here on the right, we have x plus 5 is equal to negative 1x minus 11. And now I'm going to work to get my like terms together. On our left equation, I'm going to subtract x to the other side. Well, 1x minus 1x is 0. Bring down the 5 equals 1x minus 1x is 0. Bring down the 11. Well, wait a minute. 5 doesn't equal 11. So there is no answer to that part of our problem. If I go over to the right side, though, the opposite of a negative 1 is a positive 1. So I'm going to add x to its other side. 1x plus 1x is 2x. I'm going to subtract 5 to its like term. 2x is equal to negative 16. Divide both sides by 2, and we get x is equal to negative 8. And so there is still a solution. It's x equals negative 8, but there's only one because of the way that our equations are set up in the math that we do. So that's not an extraneous solution, and there isn't one in this problem. There's just one solution that ends up to not be possible. Now, we can have x equal to a negative number. So if I plug in that negative 8, negative 8 plus 3 is negative 5. Negative 8, sorry, let me go back. I apologize. I did that exactly backwards. So 5, and that's a negative 3. Negative 8 plus 11 is a positive 3. The absolute value of negative 3 is 3. the absolute value of positive 3 is 3, and 3 equals 3 is good. All right, if you would try number 18 and 20. That's it for this set of notes. Have a great rest of your evening.